Good.
Okay, thanks. Okay, I think it's already time. So I welcome everybody on our 10 lecture of astrochemical lecture course. The lecture will be given by Professor Wolf Geppert from Stockholm University, and he will speak about laboratory astrochemistry and the processes in the gas phase. So please, Wolf, the floor is yours.
Many thanks. Many thanks to all you are coming. I hope that lab astrochemistry doesn't really frighten you away. I mean, there are lots of things you can learn from the lab, and I have been now doing this for 20 years and still find it exciting. You have probably heard about one of the questions that we really ask ourselves is, how do the complex organic molecules come to Earth? Is it by accretion under the formation of the solar system? Is it by delivery through asteroid, meteorites, or comet impacts? Or can they be formed in situ on Earth in the primeval soup, which was consisting the oceans, or in the atmospheres? That's a big question. And in the 50s, we thought we had the answer to this question, because we had a gas mixture in the very famous Urey-Miller experiment, which resembled Jupiter's atmosphere. And this gas mixture of ammoniac, water, methane, and hydrogen here was subjected to an electrical discharge. And as you all have heard, when you do this experiment, then you actually end up with the formation of amino acids and nucleobases. So the building blocks of life you can produce by this experiment, which you see here with the discharge. There are, unfortunately, some problems with this Urey-Miller experiment. And for example, amino acids and sugars, they tend to exist in two distinctive forms, namely the L and the D form. And without one exception, you have these two forms of every amino acid that life uses, and life uses only this form, the L form. The other form, which is actually the mirror image of that, is completely useless for life. In the Urey-Miller experiment, you get equal amounts of both forms, what we chemists call a racemate. And as I said, life only uses one of these two forms. So the question is now, how did this homochirality, as we call it, emerge? And one of the other problems we have with the Urey-Miller experiment is that the synthesis of biomolecules is impeded by traces of oxygen. And there are huge debates going on how much oxygen did the primeval atmosphere of the Earth contain. So there is actually some question marks to that. A possibility is that biomolecules were coming from space. And luckily, some amino acids have been found in Murchison and other meteorites, and they have actually an excess of the correct L form, which is used by life. And this enantiomeric excess, as we chemists call it, can be in some meteorites up to 20%. So in Murchison, they had to have a 20% enantiomeric excess. Meteorites are probably, as you know, named after the post station where they are found, nearest post station where they're found, and that was, in this case of this meteorite, was Murchison in Victoria in Australia. Now, if we can obviously form molecules in space, the question is how we can do it and how we can find out how it is done. Because you think that chemistry has a bad start in the interstellar medium and in space. Because if you look at the left, you see the astronomers' periodic table, and the vast majority of the universe consists simply of hydrogen. There is some helium, which is a noble gas, chemically inert, so it doesn't really do a lot, but it plays a role in the chemistry of the early universe. There are these C and O, which are the most important molecules for life. And you have some things like magnesium, silicon, sulfur, argon, and iron. But it's not really the main components. So you might think that space is an odd place for chemistry. Not only because you have mostly hydrogen and helium, but you also have very low temperatures. You also have a very low particle density in the interstellar medium. So even in dark clouds, you get not more than 10 to the 6, 10 to the 7 particles per cubic centimeter. Then simple atom reactions, which would be possible on Earth, they fail because the molecule has to dispense somehow the radiative energy and also the momentum. And this is difficult in space when the density is so low. So it is not really a good head start for chemistry. And if you form some molecules, the UV radiation from stars destroys the reaction products. So alpha Eddington can be forgiven in saying that there is no conceivable way that molecules could exist in abundance in space. And sometimes even the best scientists have to eat the words, because as you have seen probably several times during this lecture course, about roughly 300 molecules now have been detected in space. So this is the list of neutral molecules, which I copied shamelessly from the Cologne database. But there are also charged molecules and particles around, mostly cations, but notably also some anions like Cn minus, C3n minus, and even very probably C5n minus you can get. Mostly there are cations, as I said, and the ion abundances in astronomical objects is often smaller than the one of the corresponding neutrals. There are exceptions to this rule. But the problems in detecting ions is that the spectroscopic data is often lacking. And so if you don't really have any spectra, you cannot really detect that, because most detections are done with radioastronomy. Complex molecules have been very much observed during the last years and decades in the interstellar medium. One really good example is aminoacetylnitrile, which can react with water by a process which is resembling the Strecker synthesis, leading to alanine, one of the most simple amino acids, and ammoniac. Also, glycolaldehyde has been found, which can be regarded as a simple carbohydrate at the same place, namely in the large molecule heimat in Sagittarius B2, which is very close to the center, actually, of the galaxy. And more of these complex molecules are to be expected to be detected due to high-performance telescopes. So, what requirements do we have for chemical reactions in the interstellar medium? First of all, you need the absence of a barrier. Because you have very low temperatures, the particles do not really have much energy, and there are no free body processes. There are also no 2-to-1 processes leading to single products. The molecules, namely, must conserve the momentum. So something like OH plus H leading to H2O, which works perfectly well on Earth, does not really work in the interstellar medium, because you have to dispose of the energy you gain by the reaction, and you have also to dispose of the momentum. Grain surface can take up the momentum of the reaction and also can take the energy. Therefore, grain surface reactions do play quite a bit of a role in the interstellar medium. And you will hear very probably very soon, or have already heard, a lecture on grain surface chemistry by Martin McCostra, and I will not really delve on that further. Being from Sweden, I cannot really pass by in mentioning the contribution of a Swedish scientist to the temperature behavior of chemical reactions. Most reactions on Earth, they have a barrier, so you have to put in some energy first to start the reaction until you get some energy out. So if you light your camping stove, you have first to put in some energy to burn the propane or the butane or what you ever use for your camping burner, and you then can, through the reaction, then get energy. But you have to first activate the reaction. You have to first to put energy. And Svante Arrhenius has found a formula empirically for the velocity of reactions. The velocity of the reactions is how much of the product C is produced per time. And this velocity is proportional to a reaction constant called K times the abundance or the concentration of the reactant A times the abundance of the reactant B in most cases. And the formula is found that K times T is equal to a reaction constant exponential to the negative activation energy you can put in, divided by Boltzmann constant times the temperature. So if you plot the logarithm of the reaction constant against the inverse temperature, which is then called a so-called Arrhenius plot, then you get this slope. And you can easily see the higher the temperature is, the faster the reaction is. So with low temperature, every reaction that has a barrier will have a low velocity. So this is actually bad for interstellar chemistry because we have low temperatures in most of the astronomic environments. But what happens when a reaction has no barrier? I will discuss that later, but you usually have number of collisions leading to reactions and an average collisional velocity. And you can then work out with a more complicated formula the reaction rate constant, which you can see here. However, what is the case when you have got the barrel-less reactions? In that case, a little bit astronomy helps us to understand it. Imagine a meteor flying past the Earth or flying close to the Earth. If the velocity has a certain amount and the distance between the direction of the flight and the parallel of this direction of the flight going to the center of Earth is quite large, well, Earth's gravitation will bend the trajectory of the meteor, but it will not hit the Earth. When the distance is very, very low between this velocity and the parallel through the Earth's center, then, of course, the gravitation will bend this meteor also, trajectory also, and it will hit the Earth. And there is a certain maximum distance where it just hits the Earth at a certain velocity. So this is always dependent on the velocity. And if you go to 3 dimensions, this maximum distance becomes just a circle with the radius r max. And this area then where this meteor has to fly through at a certain velocity to just be able to hit the Earth is the so-called cross-section. So now, if you go to chemical reactions, we have got a similar picture. instead of the gravitational field, you just have the attractive field between the reactants. And you have, again, a maximum distance between the parallel going through the other reaction partner, at which this reaction partner shown in red can just not hit the other partner, but form a chemical bond. And again, we have got a cross-section defined at sigma is R max square P, and it depends on the velocity or the kinetic energy of the reactants and also the potential curve. So that is clear. The stronger the attractive force between these two reactant partners is, the higher the cross section will be. When you look at this in the dependence of temperature, you will find out the lower the temperature is, the lower the kinetic energy of the reaction particles will be, and therefore the lower velocity will be, and therefore the reaction will work better when temperatures are low. So in case of reactions that don't exhibit a barrier, they work better, they are faster at lower temperatures. So this is then a modified Langevin equation, so where then the reaction rate constant is dependent on a constant times T to minus alpha, and this alpha is about 0.5. So when you have tables of astrochemical reactions, they usually have the constant alpha, beta, and gamma. So K is then defined as alpha times T divided by 300 exponential to beta and exponential to minus gamma times T. So if beta is 0, you have the Arrhenius equation. If gamma is 0, you have got the so-called Langevin behavior. So which reactions do we have in the interstellar medium and planetary ionospheres? Neutral reaction between closed shell molecules, they don't really work very well because these usually have very high activation energies and are not feasible at low temperatures. Neutral radical and radical-radical reactions, they often do not have an activation barrier. They are feasible down to very low temperatures. Ion-electron, ion-ion, and ion-neutral reactions, they often have no activation energy. So these work also. And we will have a look of these. For example, if you compare an ion-neutral reaction, which has a barrier, so the activation energy is shown, for example, here. So you start from the reactants, you form an intermediate cluster, then you have to surmount the activation energy, then you form an exit cluster between this fragment and the products, and this can then split off. So even if you look at the potential energy along the reaction coordinate, then you have got, even if the reaction in total leads to a yield of energy, then you still have to surmount this reaction barrier. So in this case, in the case where you have got an ion molecule reaction, for example, you might then have a barrier which is lower than the energies of the reactants. So the reactants can form an initial cluster. Then the molecule or the system has to surmount the reaction rate, and there is an exit cluster which can dissociate into the products. So in the case of neutral reactions, they often have activation energy barriers and show the Arrhenius behavior. And In case of ion-neutral reactions, they are mostly dependent, inversely dependent on the temperature or temperature independent, can also be, and they are feasible at low temperatures. When you look at ionic processes, then there are three different processes which are important. Ion-neutral reactions, for example, this one leading to CH+. Ion-electron reactions for most interstellar ions, that means dissociative recombination. And ion-ion reactions, which means mutual neutralizations, where a cation reacts with an anion, leading to CH plus CH4. In dark clouds, the timescales for the reactions of molecular ions is about 10 to the 9 years, divided by the number of H2 in per cubic centimeter. And if there is a reaction with electrons, this is even faster. And if there is a fast reaction with neutrals, also this can compete with the reaction of H2. Reactions of ions with other neutrals are only important if the ion does not react or reacts very slowly with molecular hydrogen, because in dark clouds, in the interstellar medium, you have got, as you have already heard surely during the lecture, a lot of H2. So there is a rich chemistry possible, but we have to have ions to begin with. So how does it start? In the interstellar medium, it starts with the production of H2 plus by cosmic rays. And these cosmic rays consist mostly of protons, a little bit alpha particles, the rest is gamma rays, muons, and electrons. And the cosmic ionization rate is about 10 to the minus 17th per second. So this is a considerably slow process because there are not so many cosmic rays around. But once you have formed the H2 plus, it reacts with H2 and forms H3 plus hydrogen. And this goes on a month's time scale. Here we're talking about a time scale of millions of years, but this is going on a months to yearly sum. And this cosmic rays were discovered actually by an Austrian, by the Nobel laureate Victor Franz Hess. So what he did is that he noticed that actually there was an ionizing radiation going on. This was very well known, but people believed, okay, this is due to the radioactivity of the Earth. But strangely enough, it did not really diminish very much when you went on the sea and did your measurements of the ionizing radiation there, because water is not very radioactive. And there were several possibilities. It could be from the Earth, but it could also come from space. And what then Victor Franz Hess did is, as is shown here, he went up with a balloon, took his electrometers over there, and he found that suddenly the cosmic radiation increased. This radiation increased with the height. So it could not emerge from the Earth, but it could still be from the sun, for example. And luckily in 1912, we had a total solar eclipse in Europe. And in Vienna, he used this to go up with the balloon during the solar eclipse and did his measurements there. And lo and behold, there was not really any significant reduction of the radiation by the solar eclipse. So it had to come from space, and the cosmic radiation was discovered. So with the cosmic radiation, you can form H3 plus. But H3 plus is important, but it's not really so exciting. But it can start ion-neutral reactions. And these ion-neutral reactions, they can consecutively lead by reactions of H3 with an atom, which I call just X at the moment, to XH plus H2, so you transfer a proton. Then the protonated X can react further with H2 leading to XH2 plus. And this game you can actually then continue for another time, leading to H3 plus, XH3 plus. And by dissociative recombination, by combining this ion with an electron, you can get XH2 plus H. So you can form your first molecule. And now I want to replace this X with oxygen, because I want to see if there can be water formed in dark clouds. Here start with H3 plus O, leading to OH plus H2, as we said. And also you can do that with H2 plus, but it's less important because H2 plus you have got less in the interstellar medium because you reacted with H2 to form H3 plus. And then you can, as I presented in the slide just before, by successive hydrogen addition, come to H3O plus. And then you do dissociative recombination, but then you are in for a not so nice surprise, because then you actually form water, which you want only 25% of the dissociative recombination events. The rest leads to other molecules which are interesting, but they are not water. This is one of the main processes where how you can produce water. You can also have the reaction of OH plus H2 leading to water, and the OH can also react otherwise. OH plus O leading to O2 plus H, and OH plus C leading to CO plus H. Also on grain surface, as Martin has surely pointed out to you, you can form water, namely by successive addition of hydrogen to oxygen. You can do that on the grain because the grain can take reaction energy and the momentum. So on grains, a lot of things worked, which are not really working in the gas phase. And you then get actually H2O, which can be photodisturbed. But in the cold clouds, the water abundances have been much lower than predicted by the models. And there has been some problem all the time, which has been solved now, more or less. When you look at another important molecule, methane, you can start again, adding H3 plus to carbon, forming CH plus, and you can do our old game of adding hydrogen from hydrogen molecules, leading to CH2 plus, CH3 plus, and then the next step, unfortunately, leading to CH4 plus does not work because it is endoergic, which means that you have to put energy to drive the process. This is not really feasible in the interstellar medium, but you can do a so-called radiative association where you merge the CH3 plus with H2 and you dispose of the momentum and the energy by sending out the photon. Finally, when you have reached CH5 plus, you can do the dissociative recombination again, but unfortunately again, that what you want is only produced at 5%. So there is not really any efficient methane formation. But you are not restricted to electrons. You can also do proton transfer. CH5 plus CO leading to HCO plus CH4. Question is, why does methane matter? It's a nice molecule. You have got a lot of it on the giant planets and also on Titan, but it's not really any organic molecule, big organic molecule yet. It's an organic molecule, but it's not really big. But by insertion of carbon, you can produce more and more complicated spaces, as I showed in this scheme. So with that, you can then get a lot of hydrocarbon chemistry. Also, binary reactions can elongate chains, so you can then get very nice molecules already, like C4H3 plus ions and HC3N, for example, which is an important molecule on Titan. And Iteratively, these reactions lead to long carbon chains with little hydrogen saturation. These have been detected in dark clouds very early already, in the early days of astrochemistry. And especially interesting is, for example, this process where you can form C3H, which has two isomers, one cyclic, one linear. Now, we know that we have processes which lead to complex molecules. So how do we investigate them? One of the very nice devices where you can do this are ion traps. The ion traps were invented by the German Nobel laureate Paul, and are called therefore Paul traps sometimes. So what is the principle of it? You put an ion in a quadrupole, and here you see the electrical field. So when it's a negatively charged cation, you have a negatively charged anion, you have, for example, here the cathode and here the anode. So the energy field will be like that the negatively charged ion wants to go down to the anode. But when it starts going down, you turn the field, you rotate the field, and then the ion suddenly adds up, not in the valley here, but on the hillside here, and will go down. And when you use the right frequency of this rotation of the field, which is usually a radio frequency field, then you can keep the ions in. And this is usually done by a 22-pole trap. Why 22 poles? That had technical reasons, but if you have multiples, then you have got a very flat field, electrical field inside here. This is good because when the field is less flat and bumps around quite a lot, then you get a heating of the ions, which you don't really want, because in the interstellar medium, you have got whole temperatures. So you want to investigate at whole low temperatures also. Here you see the effective potential of this ion trap. This is the radius divided by the radius of the ion trap in total. So if you have a quadrupole, you have got quite a steep field, and when you go to the 22-pole trap, you have got a very flat field quite throughout the ion trap, and that's a good thing to have. So this is how these ion traps look like. They have about length of 5 centimeters or something like that. And here you can see the rods where you can actually catch the ions radially. Axially, you have got some plates here which you can charge for anions, for example, negatively, so that they confine these ions also in the axial sense. So what you can actually look at in these ion traps are reactions like the deuteration of H3+. So you see when you follow the ions in the ion trap, you take probes also from the ion traps at regular intervals. So you see that the H3+ is diminishing because of this reaction where you react H3+ with Hd and you exchange hydrogen with deuterium. So you get the decay of the H3+, and then you get first the buildup of H2D, here shown, but then it goes down again because it is consumed. First it's produced by Hd, and then it goes down because it's also consumed. And finally, you get the slow build-up of the D3+. So with these ion traps, you can investigate such systems. So how does these machines work? You usually get in the ions by an ion deflector. You catch them, you put in a buffer gas to cool them, and then you add your reactant gas from a pulsed valve and let your reaction happen. And after a certain time, you open the trap, extract the ions, and actually measure the ions. So this is, for example, shown here for the reaction of CH3 plus H2O. And why is this important? Because with this, you can actually form CH5O plus. And there is a ternary process, which involves the noble gas, the buffer gas, but there is also a cut-off at the abscissa, which is the radiative process, where you actually add to water to CH3 plus to form CH5O plus and yielding a photon. Yeah, these reactions are not only important in the interstellar medium. They are also important in Titan's atmosphere. And I will give you a very short introduction into that. Titan is a satellite of Saturn, and it has been found that it has an atmosphere. And this was first discovered by Joseph Solar. And he could see, when he observed Titan with a telescope, that the edge of the moon is darker than the center of the moon if you look at it. And this usually points to an atmosphere, because at the edge, the light coming to us has to go through a thicker layer of the atmosphere. And the problem was, Joseph Kumar Solar had very good eyesight, and this time you actually really observed with your eyes and then made drawings which you can see. But people could not reproduce it because they hadn't had his eyesight. So that meant that people did not really believe that. And it was first in 1944 where Kuiper found very thick methane lines in Titan's atmosphere with the Mount Palomar telescope in California. And therefore, he could find out that actually Titan has a methane atmosphere. Interestingly, Titan's atmosphere very closely, in many cases, resembles the one of Earth. It has a similar surface pressure, about 147 kilopascals. It is nitrogen dominated. It could maybe resemble the atmosphere of early Earth. People do not really tend to believe that's too much after new results, but I mean, it cannot really be 100% excluded still. It has traces of hydrocarbons and nitrogen compounds. And interestingly, the mixing region, so where you still have a good mixture of the whole atmosphere, is extended to higher altitudes. The so-called homopause on Earth, where the mixing is finishing, is at 85 kilometers altitude. On Titan, it goes up to 1195 kilometer altitude. And due to this nitrogen, hydrocarbon, methane atmosphere, you can form radicals and ions in this atmosphere. And you start, for example, with magnetospheric electrons, because Titan is usually embedded in the magnetosphere of Saturn, and you can start forming long-lived excited state of nitrogen and also the ordinary nitrogen atoms. You can also form CH3 plus by impact of these electrons, CH4 plus, and CH4 plus easily donates protons to CH4 to lead to CH5 plus. So you get two hydrocarbon ions in the primary processes, CH5 plus and CH3 plus, either by direct reactions or by transformation from CH4 plus. Then you have UV photons from the sun, not so much as on Earth because Titan is much more distant, but it's enough also to produce highly excited nitrogen. And also from methane, you can do UV photolysis and produce CH2 and CH and CH3. So I've got a lot of reactive substances to start. And for this, you can then produce further complicated molecules. For example, from CH3 plus CH4 leading to C2H5, which then can recombine with an electron leading to C2H4 plus H. Only 12% of the instances that happens. The other processes lead to other products. But nevertheless, you can also react then C2H5 plus with this newly formed C2H4 and then get C3H5 plus. And by electron dissociative recombination, you can then form C3H4 plus, alane or methylacetylene. And also radical neutral reactions are important, namely N2D, leading to C2H4, which leads to CH3CN plus H. I was talking about the magnetospheric electrons. Here you can actually see what we're doing. So this Titan is embedded here in this magnetosphere, and the magnetospheric flow of electrons actually hits then Titan's surface, a little bit deflected by magnetic fields. Titan has not really an own magnetic field, but it distorts the magnetic field of the magnetosphere of Saturn, and therefore you can actually get hit. The atmosphere gets hit by magnetospheric electrons. People wanted always to model these atmospheres, and there are people very active in that. And what in the models you assume an equilibrium, or better said, a stationary state between production and decay of the ion Ne. And on the production side, you have the ionization rate, the cross-section here, sigma of the ionization from an ion leading to, from a neutral leading to a cation and electron. Also, there are transfer processes where you can transfer the charge or transfer a proton. So this can lead to production of ions. And for the loss, you have, of course, the dissociative recombination, as I have shown, and also the transfer of charges or charged particles from one ion to another can lead to a loss of this ion. The problem with models is they work after the GIGO principle, which means garbage in, garbage out. And in earlier models of Titan's atmosphere, people thought that mostly protonated hydrocarbons are formed. And this is an older model by Atrea. And you can see here that very little nitrogen-containing chemistry was found. This was challenged then by the ion-neutral mass spectrometer on board of the Cassini. The Cassini ion-neutral mass spectrometer had two operating modes, one open source modes for ions and one closed source modes for neutral. So you see here this open source where the ions can come in. They are then bent in by this quadrupole switching length and then analyzed by the quadrupole mass analyzer shown here. Whereas the ions can be caught, the neutrals can be caught in a closed antechamber, and then they are transferred to a source where they are hit by electrons and then ionized, and then the produced ions can then be analyzed by the mass spectrometer. And even very shortly after Cassini has reached titan, it was found out that you really do need nitrogen compounds to explain the mass spectrum. Because here you have the found abundances of the ions in densities per cubic centimeter in Titan's ionosphere. If you do a fit without including the nitrogen-containing anions, you fail sometimes very grossly here, a factor of 10 or 10 to the third. This is not even acceptable for astronomers, so you have to put in nitrogen-containing compounds. And one important nitrogen-containing compounds, class of nitrogen compounds is nitriles. The nitriles can be found in atmospheres. There is a rich nitrile chemistry in Titan's atmosphere. And these nitriles can be the first steps to biomolecules because they have nitrogen and they have carbon and can react further on to form amino acids, to form nucleobases. They can also polymerize with H10, for example, to so-called phollines that are orange, brownish looking substances. The word pholline comes from the word mud, pholos in Greek, and these phollines are thought to make up the orange-colored haze layer that Titan has. And if you do that with HCN and some other nitriles, like shown here, RCN, in the lab, then you get a very good resemblance of the color of these phollines you produce in the lab and the color that you get from Titan's haze layer. Unfortunately, these nitriles, so these cyano compounds with an CN group, they are destroyed mainly by protonation and dissociative recombination. And when you do that with most of these, then the dissociative recombination again gives you back the nitrile. So you get actually a proton on top of that nitrile, and then you recombine with the electron, you kick out the hydrogen, and you end up with the nitrile again. So you don't really gain too much. Anyway, Titan is not the only place where they have nitriles. There is also the interstellar medium, where very early already nitriles have been found, like methylcyanide by Salomon, methyl isocyanide, cyanomethyl radicals, and cyanomethylene radical, for example. They were detected quite early, as you can see. And so you have quite a lot of nitriles found. The question is, how can we see then reactions of these substances? And how can we detect the products of this and the pathways these reactions do, leading to nitrogen-containing compounds or leading to destruction of such substances like nitriles? And that I would like to talk about in the second part of the lecture. I think it's a good idea now to have a maybe 10 minutes break. So maybe a little bit more generous so that we can meet again at 3 o'clock. So I'm looking forward to see you again and at 3 o'clock.
Okay. So we will come back at 4.
Sorry, at 4 o'clock, yes. I apologize, I have been on the wrong time zone. It's 4 o'clock Central European time. But I can say it's 3 o'clock UTC, which astronomers use. So, Sergey, can you hear me all right?
Yes, yes.
Okay.
Wolf, super. Yeah, you
So
can
it's
continue.
now 4 o'clock sharp, so we start again. I go back to this slide again because I said to you that nitriles, or cyano compounds, CN compounds, they are very chemically inert. That is correct, but there is a possible exception, namely CH2CN plus, and we did some experiments with that, which I want to present because they are somewhat instructive. CH2CN is a possible reactive cyanointermediate to build larger molecules. And the mass 40 has been detected with the ion neutral mass spectrometer, and most likely it's due to C2H2N+. You don't really have so much argon 40 on titanium. The model calculations predict a density of 13 per cubic centimeters at the peak of Titan's atmosphere, 1125 kilometers altitude. And in previous models without nitrogen compounds, this peak has been underestimated. And this CH2CN could actually react with unsaturated hydrocarbons, form template for larger molecules, and then actually lead to phthalates. How do we investigate that? You can actually do that with a guided beam mass spectrometer. How does this work? You have an ion source where you produce the ions by electron impact or electrospray. Then you actually transfer the ions to the first octapole where you add a cooling gas. And then you have the reactant ions selected by the first quadrupole, mass selected. Then in the second octapole, you add the reactant gas, and then the products, which are shown in yellow here, are then by the second quadrupole mass selected to be detected. So you get a mass spectrum of the products. Interestingly, when you form these ions, the CH2 Cn plus ions, you can do that by electron impact ionization of chloroacetonitrile, which you can buy at companies. And with this electron impact ionization, you can form then CH2Cn plus. The thing is that, unfortunately or fortunately, because it makes the system more interesting, it forms these it forms 4 different isomers. And there has been some discussion about the energy, relative energy of these 4 isomers. There is a cyclic one, the acerine cation, the CH2Cn plus, which you can see here. And these two, this is CH2NC plus, and the linear one. And newer calculation actually predict that this order of these two is inverse, but they all agree that the cyclic one is the most stable one. Isomers in interstellar and ionospheric chemistry have been long on the radar screen of astrochemists. And the increasing molecular complexity augments the number of possible isomers. And even rotamers, so isomers created by rotation via single bonds, can actually function as distinctive species in low temperature environments because these have different radio frequency spectra, and under interstellar conditions, the barriers between these isomers might be too high to amount it. So you have to treat or even rotational isomers sometimes as different species in the interstellar medium. What you want, of course, as a chemist to do is to selectively produce isomeric ions. And you select an apt precursor molecules, which can lead selectively to one different isomer. For example, electron impact ionization of acetonitrile leads to the cyclic cation, which we have seen, and the CH2Cn. When you do that with CH2Cn, you only get the CH2Cn plus. And photodissociative ionization using synchrotron radiation of CH3 plus at lower energies can actually deliver only acerine plus cation because the energy is not enough to produce that one. So you have possibilities to isomerically select. And then you react this CH2Cn plus with different hydrocarbons. For example, with C2H2, and then you can get products like CH3 plus HC3N. And if you plot then the density of the reactant, in this case C2H2, versus the intensity of product ions you observe. In the case you have a primary product, you get a nice pseudo first order reaction, and you get a linear plot. The crux is, however, that these molecules like this CH3 plus can react on with the C2H2 and form secondary products. In this case, however, you get a quadratic pressure dependence on the acetylene pressure. So you can distinguish between primary and secondary products in the lab by looking at the dependence of the product yield on the neutral reaction partner. You can also work with deuterated isotopomers to distinguish between different products, channels leading to similar masses. Sometimes, products have similar masses, and also to identify main product pathways and their thermodynamics. So we did actually studies with both the deuterated acetylene and the deuterated substance. And there you can distinguish between different products. For example, if you look at a light isomer, you get the mass product of C2H2 plus or Cn plus. Both have mass 26. So you can't distinguish between them. But of course, in the case you work then with C2H2, C2D2, then you should get actually the respective mass when you use the deuterated method, namely 28. And if you work with the deuteronated acetonitrile as a precursor and the deuteronated ion, you should actually then get also the mass 26 as it is seen here, because it's simply a charge transfer to this neutral. And that's what you see. So you see, in the case you work with the deuteronated methane, the ethylene, you see mass 28, whereas when you work with light isotopomers, you see mass 26. So you know that this is the product, and not the Cn plus, because then you should actually always see mass 26. These are the possible reactions. And of course, you want to see what's actually happening. And to distinguish reactions that are with a barrier or without a barrier, you can do ab initio calculations, and you get a certain potential surface. So you see here the minima, which are intermediates, sorry about that, and you see the transition states between. And when you do this calculation, you find out that you get only 3 product pathways in this system, namely C3H3 plus, C4H2N plus, and C3 plus. So these 3 product channels you get. This one here is energetically possible, leading to HCnH plus, but we found out that this is actually the formation of this ion is produced by collisional induced dissociations only at high energies, a process which is not that relevant for the interstellar medium. So this is the very complicated reaction pathways which we had to calculate out. But I can tell you just the bottom line that you get C3H3 plus HCN, C4H2N plus H2, and CH3 plus HC3N. The question is, okay, this is fine. We have the different isomers. We see the different isomers in our experiment. We can even see that isomers are reacting differently. But is this correct? Do we really have these isomers? And for that, you can actually do spectroscopy. In the old-fashioned absorption spectroscopy, you have got a radiation source, tunable, monochromatic easily. You have an absorption cell, and you have got the broadband photon detector. You need very high number densities. And this is very difficult for ions, and it's extremely difficult for reactive ions. And you also can get contaminations, because not very often your ions in an absorption cell will be pure. However, when you work in ion traps, where you do mass selection, you are very sensitive. You can isolate the reactive ions. You can actually work with low ion temperatures, which means less congested spectra, higher signal to noise. And you can also work at long interaction times, because you can really catch these ions in the ion trap for a very long time. So how do you distinguish between isomers? You can actually use tagging of the molecular ions with noble gas. So you add a molecular ion and add a noble gas, and the noble gas atoms can then attach to these ions. You irradiate them with the laser, and if you have a resonance of a vibration mode of the ion, there's excitation of the vibration leads to cluster destruction, so loss of ion signals. And you can both establish the identity of the ions with the spectrum and the relative abundance. And you compare the assignments of your vibrational lines with the initial calculation. So that's how things work. So you add the ions from an ion source, mass select them in, band them into the ion trap, and then add a helium or a neon pulse to actually tag these ions. So here you have got the ion, and here you have got the neon or helium atom, which is attached to that. So when you go from the ground state of this attached ion with an infrared to an excited vibrational state, since the binding energies of noble gases are very low to these ions, this will dissociate and you will get a loss of this signal from this cluster and an increase of the signal of H+. And then you see a spectrum where you get a depletion for each vibrational normal mode. And you need very powerful lasers for doing that, and that's why we're working on the free electron laser in Nijmegen in the Netherlands to do that. And then you can also shoot a lot of different laser pulses at the same ions that you actually get rid of all the ion clusters. And if you do that, you can actually distinguish if you have one or two isomers. If you have got only one isomers and you go to a line of the vibration and you shoot a lot of laser pulses with the light, then you will just get rid of all the clusters or of all the tagged ions, and then you get no ions at all. So the depletion, actually the loss of the ions, will be one. Of course, when you have two isomers, you only deplete the ion to which this wavelength or wave number of the laser corresponds to. The other one is left in peace by the laser. So if you get two isomers, you get an asymptotic line towards the number of towards the share of your ion you are depleting in the trap. So if you have got two isomers, you get a lower relative depletion, and from that you can work out how much of these isomers you have. So that was done for CH2Cn+. So you can actually see the spectrum of this. When you use different precursors, you get different products, as I said. And you see here the lines from the acyrenyl, the ring-formed cation, and also from the cyanomethyl, and you see also a little bit of the isocyanomethyl cation. So you get three different isomers. So what you can conclude is that in the reaction of CH2Cn+ with acetylene, you can form larger nitrogen-containing entities, which is important because this can lead further on to more complicated ions and neutrals in Titan's atmosphere. There are several parallel reaction pathways for CH2Cn+. The linear one. The cyclic one only leads to C3H3. Sorry about that. It's not C2H3, it's C3H3. The cyanopropyl cation could act as a template for build-up of larger entities. Isomerism is a problem. Photoionization through synchrotron radiation can lead to selected isomeric species. We have probably hot species, so ion trap and VOV. Photoionization studies are therefore envisaged and partly performed. So what is the implication for Titan's atmosphere? The formation of C3H3 plus is not really extremely relevant. There are many routes to C3H3. There might be a small contribution to HCCCN, which has been observed on titan by our reaction. But most important is this one, because it leads to cyanopropenyl ion. And this can actually be a template and act as a template for further build-up of larger molecules. Why is this relevant for the atmosphere? In the Urey-Miller experiment, amino acids are formed in the liquids. There are pholines also generated, and this leads to amino acids. And with water, you can actually form amino acids then from these pholines, which are formed in this. This could be a feasible process on other celestial bodies and could actually happen on an exoplanet where you have got a nitrogen-dominated atmosphere. How could this go on? You can actually form pholines, HCN, in titan, which we know it happens. By hydrolysis, you can get actually pyrimidines and amino acids. And of course, you have got a very, very long way to go to autocatalytic systems, to information storage molecules like DNA and RNA, and very long time you have to go until you get to humans. So that is what I wanted to say about ion-neutral reactions. Of course, there are actually also ion-electron reactions, and these can be investigated by storage rings. You can form in a storage ring the ions in the source, mass select them by binding magnets. You actually inject the ions with a radio frequency protocol and accelerate them, merge them with electron beam, and detect the neutral products. And the merger of the ion beam with the electron beam is performed in a so-called electron cooler. So you have the ion beam here. You have a cooled cathode producing the electron beam. Then the electron beam is bent in here and goes parallel, merged with the ion beam for a certain time. Then reaction can happen. Electrons can recombine with ions and lead to neutral fragments, which are not affected by the bending magnets, but then leave the ring tangentially. So what you get here is an electron with an ion. It breaks up, but then they hit the detector almost simultaneously. So you get only one electron pulse, which all events leading to a full mass signal, because they are hitting the detector at the same time. You can, of course, get an information about particle loss if you're losing something on the way. The pattern changes when you put in a grid. And this grid holds up about 0.3, 30% of the neutral products. So if a certain probability of only one of the reactant products passing through, or all passing through, and this here then splits up into a fragment energy spectrum signal, where you see the different fragments. And by mathematically simply converting this, can convert it into a branching ratio. So this is, for example, a fragment energy spectrum of the dissociative recombination of protonated methanol. And when you look at this protonated methanol reacting with oxygen, you have the reaction pathways here, and it's found out again, so that what you want, the methanol, you only get with a branching ratio of 3%. So a surprising result, which you find in these electron-ion reactions. I will also shortly touch a little bit on ion-ion reactions. We have got a new storage ring in Stockholm on that, where you can actually store in an electrostatic storage ring ions of opposite charge. For example, you can store cations here in this ring and anions in this ring. And in this merger section, you can actually allow them to recombine, to react with each other and form neutrals. This double electrostatic storage ring, Desiree, has several advantages. You can easily produce the ions by different sources. This charges electrospace. You can efficiently cool down to several Kelvin. There are very low rest gas pressures. Long lifetimes of ions can be several hundred seconds and more. You can efficiently detect neutral products, and you can do lifetime measurements by repeatedly probing the stored ion beams through photodetachments by laser pulses in the case of negatively charged ions, for example. And that's what we did for CH- ions here. That was what I wanted to say about ion reactions. I will use the last part to do a bit on neutral-neutral reactions. And you have the possibility to measure these neutral-neutral reactions in the condensed phase or in the gas phase. In the condensed phase, you have a high density of probe species, which is usually a good thing to have. You are in the thermal equilibrium with the environment, so efficient cooling. But unfortunately, get lots of third-body processes which are not relevant for the interstellar medium and high layers of atmospheres. We have got radicals and most ions rapidly destroyed in most environments, which are high density. And the conditions are, as I said, are largely irrelevant for the interstellar medium. But what you can do is to do a trick, namely adiabatic expansion. Expand the species through a nozzle into a vacuum. And there is no heat transfer from the gas to the environment and vice versa. So it's called an adiabatic process. And in real gases, there is a cooling with expansion. Because if you expand a gas, then the gas molecules have to surmount their mutual attraction. And that costs energy. And that's why, for example, when you put a shaving foam on your hand, it's cold because the shaving foam expands, and then the gas molecules in there, they have to surmount the attractive force, and that goes on the cost of the thermal energy. So you have then a gas expanding here. There is a low transversal and high longitudinal cooling, because when you let these expand here, they will have the same velocity. Like if you're in a traffic jam, every car has to go with the same velocity. And there is an additional benefit that you get the universal constant velocity through these collisions in the orifice. So you select only these which are going out that way, which have a velocity compound out that way. So you have got the high transversal cooling because you only select the gas molecules with a low transversal energy component, and then you also have a longitudinal cooling by collisions in the orifice. So such a cooling for adiabatic cooling can be seen here when you are looking at hypersonic jets. So by the expansion of the gases, the exhaust gases coming from the exhaust of the plane, you actually see a condensation of water forming a small cloud here because of the adiabatic expansion cooling of the exhaust fumes of the aircraft. So you get actually the formation of a disk with constant velocity. And that's what you see here, because normally in a gas, the velocity the distribution of the different gas molecules is very broad, follows the Maxwell-Boltzmann statistics. Whereas when you work with an expansion, you can actually create a supersonic beam which has a very sharp profile. And that's good for the experimental accuracy. So you can cool the translational energy in supersonic beams very efficiently because you have a continuum of energies. With the rotational and vibrational quanta, where with a rotational energy, you've got energy quanta. Their cooling through collisions is fairly efficient. The rotational temperature is then about 330 to 90 Kelvin. In vibrational energy, you have got quite large energy quanta. So cooling for collisions is not very efficient. So the vibrational temperature is usually larger than 100 Kelvin. So this is actually what you get in a supersonic expansion. Here you have got a very constant velocity flow, which is supersonic. Then here you have got actually the area where you can get sonic. So you will get a non-uniform flow, a turbulent flow here, but here you have got a very constant, very uniform flow, and that you can use that for experiment. So for achieving that, you actually use a so-called Laval nozzle. This is something that is also used on spacecrafts, by the way. And there is the uniform supersonic flow can then have temperatures from 7 to 220 Kelvin, dependent on the geometry only of the Laval nozzle. So therefore, you need, for each temperature, you need a special Laval nozzle, but you can also then pin down the temperature by using different Laval nozzles. For using this for experiment, the Crécy technique has been developed. Crécy means the French acronym for cinétique de réaction and écoulement, supersonic uniform. You can have very low temperatures at thermal equilibrium. Temperature and density are constant. There is an ultra-cold wall-less reaction vessel because the supersonic beam has no walls. Cooling is rapid without the condensation. The disadvantage is you need very strong pumps and loads of gases. And as I said, you need a different nozzle for each temperature. So that's how the experiment is done. You have got, for example, you want to establish the reaction of CH plus CO. You put in bromoform, which is tribromomethane. And by this 266 nanometers laser, you actually break up the bromoform and produce CO. And then you add the CO into the reaction chamber. And then you see the reaction happening here in the expansion, and you follow the products or the reduction of the reactants by this dye laser, by photofluorescence, for example, induced by this dye laser, and by moving the relative distance between the nozzle and the detection photomultiplier, you can follow the reaction along the flow. So you get a reaction velocity out of that by following the reaction along the flow. This is the Cressure apparatus in RAN. So you see this huge exhaust leading to the exhaust pumps. These exhaust pumps are very massive and they make quite a lot of noise. That's why they keep them in a cellar. And then you get a first order decay from the laser-induced fluorescence signal from, for example, CH in the presence of CO. And when you work out that, you get a decay, and you then can work at different gas densities, and you get different decays dependent of reactant gas densities. And if you plot them as a first order plot, you can then here get the pure reaction rate of COH plus CO. That you can do, for example, with carbon plus O2, where you get a very nice barrel-less reaction, a reaction rate constant which diminishes with increasing temperature. Also, carbon 3p with hydrocarbons you can investigate, and you see all these reactions of carbon with hydrocarbons are almost Fermi-neutral, and you can form also cyanoproteins with reactions of acetylene or hydrocarbons, NCN, or also other compounds with C2H. And as you can see here, you see the formation of this product, the chain elongation by reaction of CN with acetylene, which is here cyanoacetylene to cyanoacetylene plus H. And you see the reactions are very efficient also at low temperatures, at the temperatures close to the interstellar medium. Yes. So what we can conclude from all of this? Ion and radical reactions have a great impact on the chemistry of planetary ionospheres, interstellar clouds, and circumstellar envelopes, as I said. So really these processes matter, and for validity of the models we get, we have to have good experimental data, branching ratios, reaction rate constants, and also barriers and energetics of this reaction. All this we need really to make good predictions. And of ions and neutrons, many different formation and destruction processes of these species exist, and the more complex they get, and we get in more complex molecules due to ALMA, James Webb Telescope, and other sophisticated observation devices. As I said, more and more complex molecules are detected in space, and these processes, which we have discussed now, are likely to play an important role in their formation. An equally important role is played by surface chemistry, which you will hear from Martin McCostra. Unfortunately, molecular data on many ion reactions and on many neutral reactions in the gas phase is still lacking, so we still have lots of work to do. But new experimental facilities like supersonic beams and flows, electrostatic storage ring, magneto-electrodynamical traps, ion traps, cross-beam machines, you name it, will enable research into these processes. So, since I was told by our moderator that there usually are quite a lot of questions, I will now leave time for questions and stop here and leave the floor open for questions and
Okay, thank you.
contributions.
Thank you, Wolf, very much for this very interesting, clear lecture. So this lecture is now open for questions. So all students are encouraged to ask questions in the chat. Please do it, but we can already start with one question which appeared during your lecture. So the question is, in early discussion of the talk, you mentioned that OH plus H cannot form H2O because of the conservation of momentum. Could you elaborate a bit more why it is the case? Could not the resultant H2O molecules just carry a net momentum?
Yes, this is an interesting point, and I would like to elaborate this a little bit more. Of course, also the molecule can have a momentum, but if you have an isolated system, like you have in the interstellar medium, you will have to actually look at this from the center of mass, in the center of mass frame. And then it is actually very difficult then, because then when in the center of mass frame, when you have the molecule formed, the formed molecule, when you treat the system isolated, has a momentum of 0. So now, I mean, you have two compounds coming in with a momentum, with both a linear and angular momentum, and then you have got a molecule which in the center of mass frame has no momentum at all. So how does it can get rid? Well, there is a possibility actually by radiating off the momentum, and we see such radiative association reactions. So where you actually get two reaction partners to reaction partners together, and then you get a highly excited intermediate product, which then can radiate off this excess energy and of course then lose also momentum. That so-called radiative association with very small systems like H plus OH, it is usually a very inefficient process because there are not so many transitions in the resulting molecules, in the resulting molecule to dispose of the energy. The more complex and the larger the systems get, the more possibility the molecule has to distribute the energy and also radiate off the energy, because in a larger and larger molecule, you have got more and more transitions, vibrational, electronic transition. So these processes can actually happen. So with large molecules, you can actually get so-called radiative associations where you distribute then the energy and radiate off the energy. But with small systems, this is fairly inefficient.
Okay.
There's another question we can see already on the chat.
Yes, before we proceed with the questions, there is one small request. Please, can you return to the last post, because I could not read. Maybe it's a summary slide. People want still to have on screen.
I try to do that. I will come back. I have to go to escape now. Yes, this is the conclusion. So I start from the current slide, which is the last one. So we have this on. So now I cannot see the chat, but I mean, this is okay. I mean,
okay, yeah, I will read now. So the next question is, why the amino acids are still not detected in the ISM?
Well, I mean, it will just be a matter of time as they are, because they are they are complex, and you also need to have a very good radio frequency spectrum, because one line detecting is no line. So you need all the lines from the molecule to be covered. You have to measure the amino acid spectrum in the gas phase, of course. And this works very nicely for the nitrites because you can evaporate them very, very easily. So with amino acids, most of them are actually destroyed when you try to evaporate them, especially the more complicated ones. So it's not really so easy to get them into the gas phase. You can work with things like electrospray, but it's quite a hell of a work to actually measure radio frequency spectra of things that are not easy to evaporate, and with things that are probably then not so abundant in your apparatus. And of course, these are fairly complicated molecules already, which have lots and lots of lines. So it's not so straightforward to assign these lines. We have been working together with Sonia Melandri from the University of Bologna, doing some spectra of aldehydes and of water clusters of these substances, but even there you're already starting to need a lot of measurements and a lot of thinking to assign these lines. But I'm very sure that in the not so near future, amino acids will be detected in the interstellar medium. It's just that you have the good radio frequency data and you have a source where they are present and a good signal to noise ratio. Also, there is one thing: in colder environments, these amino acids, they are very likely to freeze out quite efficiently on the surface of grains. Martin McCoster will surely mention all these processes, and therefore you have got them in cold environments, mostly in the solid phase and not in the gas phase, where you want to have them.
Okay, thank you. Yeah, actually, it was also my question to clarify this point. Is it possible that one of possible explanations that most of the amino acids in space are actually in the solid state and not in the gas phase, and that's the reason? Okay.
That can be, but you also have the possibility to look at star-forming regions, protoplanetary disk, and hot cores, where you can evaporate things again. And the question is, how efficient is the evaporation, and how are these compounds destroyed by evaporation? So that is all playing in. But I'm very optimistic that we can have surely soon the first detections of amino acids. One of them there has been a claim this detection, namely the glycine, which is the most simple amino acid, and it's actually the only one which you can really efficiently evaporate. And there has been studies by Steve Charnley, who already 15 years ago or so has actually found 20 years ago found lines of glycine that was immediately debated because some people thought that there were some acetone lines. And now he has been more vindicated. So it looks like that we actually can be fairly positive that we have glycine in space and detected, but the other 23 amino acids which we're using, they are still not really confirmed detected.
Okay, this is great. Thank you. So we have a next question. I was wondering if it is possible to measure reactions initiated by H3+ with any low temperature techniques like ion traps, storage rings, or Kreisel?
Well, the ion traps, the answer is an unmitigated yes, because it has been done. I mean, I've shown you that actually the reactions of the titration with H3 plus, and H3 plus is fairly easy to produce, fairly easy to mass select. So in ions, it actually works. There is nothing that prevents you from doing ion measurements in the Crécy also. The problem is that you have to produce the ions, and you actually have to follow the ions with a photon with a laser-induced fluorescence, for example, where you don't really have any lines, I think, in the H3 plus to follow them, which makes life a little bit more difficult. But there are transitions which you can use, and so also with Gaussian, there should not really be any problem. What was the third technique that was? There was a third technique was mentioned also in the question. Which was it?
Okay, yes, Kreisel.
Kreisel, that was mentioned. So there is nothing really that prevents actually the study of ion reactions in Kreisel also. And what was the third one? Ion traps, Kreisel.
Ion traps, storage rings, or Kreisel?
Well, with storage rings, I mean, we have the possibility to definitely do that in this array, and will do so, because there are lots of different reactions which are interesting. The thing is that H3 plus tends then to react with many substances with proton transfer. So you have, in many cases, probably proton transfer as the only pathway, which makes it a little bit less interesting. But then we definitely can do that with this array, no problem.
Okay, thank you. The next question. Earlier in the talk, you mentioned the ion molecular reactions that efficiently form unsaturated hydrocarbons in the ISM and Titan's atmosphere.
Yeah.
I believe a number of more saturated molecules have been detected in these regions. Are there any major theories for how these species form?
Yeah, of course, you get also saturated compounds. I mean, you can also, as in the case of CH4 is the textbook example, you can form that you can form that in the interstellar medium also by dissociative recombination. You can form these saturated compounds by reactions of ions and neutrals, followed by dissociative recombination. This is not any hindrance. You can also form saturated compounds by surface reactions of carbon with, or carbon compounds with hydrogen. For example, methanol and ethanol are produced on surfaces. They are saturated compounds, so they can be formed from CO, for example, and other compounds by adding hydrogen to them. So this is definitely possible. On Titan, you have got quite a lot of hydrocarbons also formed by such processes, and which are even in hydrocarbon, forming hydrocarbon lakes on the surfaces of Titan. So you have got quite a lot of different saturated hydrocarbons on Titan, which can also be formed by gas phase reactions, both from neutrals, but also from ions, followed by dissociative recombination.
Okay, thank you. The next question, could you please recommend any resources for learning more about key instruments and technological tools for lab or research in astrochemistry. I was intrigued by the mentioning of synchrotron for astrochemistry. Can you recommend any papers or books to explore further in this area?
Yes, we actually have done also work on using synchrotron radiation, but we use the synchrotron radiation for production of selective production of ions. So, there we will. You can actually, there is actually, mostly it's the group at Saclay which is involved, Roland Tisson and Christian Alcaraz. But you can also, there are also some papers where I have been already using synchrotron radiation to produce ions. That has been done. Other for the detection of different isomers in Felix, there are the papers by Sandra Brünken, and there are also some other scientists which are quoted there. Stefan Schlemmer is doing quite a lot of work. There are also other scientists. So I mean, these people you can actually Google for, and you can actually also in Google Scholar and in some other sources either quote these people, or you can also go on Felix isomers. Then you find quite a lot of area of people, because the people in Cologne and especially also in Nijmegen, they have been very productive in this field, and I have been part of also some of the experiments.
Okay, thank you. So the next question. In the discussed reactions, free electrons can participate. What is the number, density, and energy range of these electrons?
The problem with electrons in the interstellar medium is that there are only indirect methods. You cannot really measure electrons because they have no spectrum. So there are only indirect measurements of the DCO plus and, for example, and HCO plus ratio. You can work out the electron density. The energy range of these electrons is also a very interesting question. On Titan, you have got the magnetospheric electrons, which are quite high in energy. They can start a lot of reactions. I think this is actually going into the kilo electron volt range, but I have to look that up. I don't really want to tell on that. And we assume that also since electrons in dark clouds can also collide with neutral molecules and be scattered, that there could be some kind of thermal equilibrium even between electrons in dense regions and the neutrals or the gas in the source in the dark clouds. Of course, electrons are also to a small extent part of the cosmic rays, and therefore you have got also high energy electrons coming into astronomical objects, but not really to such a big extent like helium plus, helium-2 plus alpha particles or protons, which make up the lion's share of cosmic rays. So you have got quite a lot of different area of electron energies. Slow electrons, more or less, maybe even in thermal equilibrium with the gas in some electron-rich regions, like photon-dominated regions, but you always get also high-energy electrons on Titan due to the magnetospheric electrons impinging, and in the interstellar medium by cosmic rays, which also partly, to a small extent, consist of electrons. And one important thing, the cosmic rays, when they impinge on molecules, they create a lot of secondary electrons with high energies. So these play also a role.
Okay, thank you. So our time approaching to the end, but I would like to ask one question still. So you mentioned that some of the molecules is difficult to produce in the gas phase. And of course, then it's difficult to measure the spectra and compare with observation. But I heard that some groups use a quantum chemical computation to obtain the spectra of these molecules, and they are of the quality that can potentially be compared with observations. Can you comment a bit on this topic?
That is correct. And we use ab initio calculations to assign our radio frequency spectra, because if you do radio frequency spectra of neutral molecules, I mean, then it's actually getting already very straightforward to do them, because the calculation of the geometries are very good. So, I mean, you can do that we have done that, for example, even water.
So can you do it?
Yes, we have done this in Bologna also, together with the people, using ab initio calculations to assign lines in rotational spectra, because in the rotational spectra you need only very good information about the geometry and the dipole moment of the thing, and then you're home and dry. With ions, it can be a little bit more difficult when they might have a more wobbly geometry, or they might be non-singlet states. Then also, when you are coming to clusters with water, for example, then the molecules actually can get a little bit more loose, which then in turn means that your predictions of the theory are not so good anymore, and even small errors of the prediction will dislocate your lines quite a lot. And of course, also the C3n minus and the C5n minus have been identified with help of ab initio calculations, because these are singlet systems. These are rigid linear molecules. So, I mean, the predictions of them will be very good. And there is the C5n minus, actually, which was identified by Paper Giannicaro with help of theoretical calculations. That still, as I am informed, if I'm not really back at the moment, is still awaiting lab measurement confirmation, but it is believed in the community that this was correctly assigned due to our initial calculations. So definitely of great help. Our initial calculations are of great help in assigning rotational spectra.
Oh, this is great. So I probably will try to contact you after regarding this topic. But we
there
still
is
have
another
one
question.
Yes, there is another question. This might be a naive question. Are the pH molecules in the gas phase or solid phase?
You can have them both. That is there have been no detections so far from the polyaromatic hydrocarbon, if you don't really include benzene as a polyaromatic hydrocarbon, but there have been detection of fullerenes in the interstellar medium, so that has been identified. So you will very probably have them both in the solid and in the gas phase, but since they are quite high, quite refractory, mostly in the form of solids, I would guess.
Okay. Thank you, Wolf, very much.
Thanks a lot for coming. I will send you then the slides today sometimes if I can, because I would I will then make a PDF file, and hopefully I can send it to you. If not, I will move it on a Google Drive or something like that and let you share it.
Okay, thank you.
And thanks you all for coming. And I
And-
hope you enjoy this course very much. And I will also like you to try to go into the website of the European Astrobiology Institute, where we have got lots of different activities for early career scientists and students. And we have also a lecture series, which is the so-called EI Academy, and which is running now and will start again in the next year in September. And please look at our web page, because you find quite a lot of interesting things. Yeah, Sergei has put it up, europeanastrobiology.eu, and we are also involved in the setup of this course. And in the name of the Institute, I will also thank all the contributors and the moderators and the people who organize this course for their effort.
Okay, I put the link in the chat so everybody can click.
Yeah.
Okay, thank you. Thank you very much.
Thank you, Sergei, for everything, and a nice evening to all.
Yeah. And see you all next Tuesday. Bye. Bye-bye.